Hello, my name is Nils Dressler and I'm an industrial PhD student from Atlas Copco at the Vehicular Systems Division at LINK-SIC University. My research is in the main field of the tightening of thread fasteners or bolted joints. This is typically done with power tools, where you can see an example here in the top right corner. More specifically, I'm looking into the control of these tightening tools. In the current phase of my research, I'm looking at the modeling of a bolted joint for dynamic tightening with the purpose of simulation and control. In this poster, I'm presenting my modeling approach to model the behavior of the threaded fastener joint when torque is applied to it. Here in the figure, you can see the schematics of my model. You can see different model components here, where I want to highlight some of them a bit more specific in this poster. The main focus on this poster is on the components which have friction involved, namely as the constant thread friction torque, the underhead friction torque, and the thread torque. All of these torque components are very similar. Here you can see an example how this model is built. You can see a variable friction coefficient as well as the clamp force dependency of the friction torque. In this picture, you can see how this model acts when you simulate it. There you have the total torque and all the components which the total torque is composed of. It's the Coulomb friction, it's the dynamic friction, you see in green, and it's the Strivik effect, which is also part of the friction. Having such a model enables studies of the tightening process with dynamic speed profiles. What you can see here is how the friction in such a system behaves if you have some noise on the system. Another interesting phenomenon is how does the torque at different clamp force behave depending on the speed you tighten it. A further phenomena which we could study with our model is stick slip behavior in the model. This can happen at different tightening speeds, but is depending on a lot of parameters. With the model, we have the option to study how these parameters impact the appearance of stick slip. Another work we have done is to estimate clamp force. This we have done by using an extended or uncentered Kalman filters, where we take the torque and the angle signal to estimate how big the clamp force is. We did this study with a master series, where you could see that the clamp force could be accurate with 95% when we estimate it. This is a very promising result because it outperforms classical estimations of the clamp force by far. We tested on different tightenings. One was the continuous drive tightening, where the extended Kalman filter worked very well. And the other one was the uncentered Kalman filter, which we tested on turbo tight, which is a tightening strategy which has a very non-linear and dynamic tightening profile. If you have any further questions, please contact me and we can have a more in-depth discussion.